Everyone, I'm Christian Pilato from Politecnico di Milano, and I'm presenting this work in collaboration with Francesco Regazzoni from the University of Amsterdam and University of Lugano. In this work, we want to use software-level abstraction for the high-level synthesis of security properties. High-level synthesis is good at optimizing classic non-functional requirements, for example, ARM power. Designers often use software abstraction for hiding implementation details to the programmers. Here you can see an example where three variables are declared as floating point, and a level synthesis generates a floating point unit that is usually quite expensive in hardware. Then using some custom data types, you can specify a custom precisions for those variables, and using, for example, operator overloading, this modification is completely transparent to the rest of the accelerator description. Then the synthesis will use an optimized unit that is less expensive. Our main question is, can we use the same approach for security properties? We use information flow tracking to motivate our work. Information flow tracking is widely used to identify misuses in software application, and also becomes interesting to apply to heterogeneous architectures. Information flow tracking associates tags, so additional variables, to selected date of an application. Then uses propagation rules to combine these additional values with the original data values to determine how the data affect the program execution, so to identify those misuses. And to identify those misuses, we need monitors to check the behaviors and the values of the tag in predefined points. So what happens in case of accelerators? Because accelerators usually have a fixed logic, so they have to be pre-designed with that information flow tracking logic. So we can use a coarse-grained approach, but this operates only at the boundaries of the accelerators, using implicit rules to combine input and output values. Or we can use fine-grained DFT to integrate the shadow logic together with the microarchitectural logic of the accelerator. Usually, this requires custom HLS tools to integrate the logic and optimize it together with the one of the accelerator. Our key observation is that the tags could be seen as additional registers or variables, and the propagation rules as additional functionalities in the accelerator. So they could be embedded in the initial code with minimal changes. These have to be integrated in a way in which the designer doesn't need to have knowledge of the security property. So we want to use a combination of a synthesizable DFT library and commercial high-level synthesis to generate accelerator with such logic. We change the definition of some variables with specific data types, where we can specify the size of the variable, but also the size of the tags and the type of the propagation rule. Then with operator overloading, we can implement those propagation rules in the library, and their integration is totally transparent to the rest of accelerator execution. Then, to check the value of the tags and identify security exceptions, we then integrate synthesizable libraries that will embed security monitors in the accelerator. Then this accelerator, with the additional logic generated by the synthesis of the library and the monitors, can be integrated in a larger architecture where those tags can be exchanged, for example, with the code executed on a CPU, where the drivers will be extended with the configuration of the tags and the identification of the security exceptions. So, code level extensions compatible with the commercial high-level synthesis is a promising way to specify and synthesize security protections. So we have seen that this is possible with information flow tracking, even though we still need to evaluate better the trade-offs of this approach compared with an approach where the accelerators are generated with modified HLS. So the main question that we want to answer in the future is which security protection can be extracted and synthesized in this way without compromising the insecurity. Thanks for your attention. This work is part of a larger project where we want to implement big data application on FPGA accelerated systems, and in this slide you can find the link if you want more information.